All right. So this, well, first of all, thanks for the invitation. I mean, we are very thrilled to be invited and also to talk to your community. It will be about LLM, Earth observation, and defining like a chatbot, let's say, for Earth observation and Earth science scientist. So I'm Nicolas Longépé. I'm with the F-lab. So we sit in Italy, nearby Rome. And together in the call, we have as well some collaborators we work with a company which is called PySchool, which is specialized in AI. And I have three colleagues, so Antonio Lopez, Jino Rohit, and then Àlex Atrio. And yeah, so let's start. Maybe Àlex, you can change for the next slide. So that could be the content for this seminar. So first, I'll give a short intro about why we need some kind of digital assistance for observation in the science. Then actually my colleague from PySchool will provide a deep dive on what we did actually to specialize general purpose LLM to the Earth observation and the science, talking about the data set that we built, how we adapted, for instance, a Mistral model to what we wanted to achieve. And then we'll present you as well the system, the overall system, an end-to-end system that can just more or less replace like ChatGPT or Mistral or whatsoever. And then we'll have a little, well, some evaluation and benchmark on the model and the system, and then a final demonstration that will be recorded to avoid the demonstration effect. But yeah, next, please, Àlex. So if you can share, please. So why we wanted from ESA side to develop a so-called digital assistant? Because I think we all practice that. I mean, it's super complicated to gather, let's say, knowledge on a particular field, especially when the field is could be narrow, for which sometimes you need some huge expertise to understand. So there's fragmentation and some signs of barrier as well to understand those specific language, either on the Earth observation, but also typical Earth science could be about, I don't know, the atmosphere, the cryosphere, whatsoever, the domain. And as well, we wanted through this project to provide to decision makers a kind of tool to understand topics and provide and to get as well some transparent and scientifically robust answers. And of course, LLM could be the right tool to do that, even though we know that LLM can hallucinate. But through this project, we wanted somehow to tackle this issue of hallucination, work on, let's say, to provide like a grounded system so that anyone can trust the system. And so this is why actually we implemented a RAG system, a retrieval augmented, so that the LLM always reason with respect to kind of trusted sources. So that's the whole idea of the challenge and then the opportunities. Next, Àlex. So with that in mind, we expect indeed that is the target and the impact to that anyone within the community, even non-expert people, can use the system, can interrogate EO knowledge, and also observation corpus of documentations. We want to provoke with this kind of system, it's a faster adoption of developed science to be faster in innovation so that you can go faster on literature review on specific fields. And again, it could be used as well for policymakers or any people making some kind of decision of all this knowledge. As of today, just as a kind of disclaimer, everything that we present today is a purely textual based information. So as of today, we do not include any, let's say, geospatial component or computer vision on Earth observation. This is typically, I mean, on our roadmap that will come in 26, but what will show up today is purely LLM and textual information based. Next, please. Just to give you a bit of like the overview of all the things that we've been doing at ESA and more specifically at the F-lab where I belong, which is kind of an innovation lab. So of course, we work a lot with the observation data set for which you need to aggregate them, make them, let's say, AI ready. So on Hugging Face, you may look at Majortom, which is as of today, maybe the largest compilation AI ready data set that exists on Earth observation, combining Sentinel-1, Sentinel-2. You have more than 60 terabytes of information, which are ready to tap in. And again, available on Hugging Face. from that, actually, we developed different geospatial foundation model. You may have heard about TerraMind, together with the colleagues from IBM in Zurich. Actually, in the coming days, we'll release as well another model, which is called Tor, which this one really enabled to have like a flexible, let's say, input patching size and embedding density. So this model is super flexible. You can ingest any modality at any resolution and with any patch size, let's say. That's the main characteristics of it. And of course, benchmarking those geospatial foundation model is super important. So this is why we implemented like the Pangea, which is kind of a standard tool to assess the situation for all these foundation model. Because for as of today, you may have like 100 foundation model initiative all over the world. So it's kind of hard for the community to understand a bit the situation. And from that, actually, from those foundation model, you can provide embeddings. You can also try to, let's say, provide those generic purpose geospatial foundation model within kind of digital assistant. But the bottleneck of that is that you need some kind of reasoning layer on top of these pure computer vision models. So this is why actually we made the first step with Eve, which has, again, as of today, like a pure LLM based, retrieving like publications, stuff like that. But the idea is really to embrace all this ecosystem of geospatial foundation model, also embeddings, and to provide like an agentic way to navigate through geospatial tools. Next, please. With that in mind, in a nutshell, this is it. It was funded by ESA, implemented by Spice School, the three guys that you see in the room. Also in collaboration with Imperative Space, which is a company based in UK, Mistral AI, because this is one of the champions that we have in Europe for LLM. And also we had an agreement with Wiley, the publisher, to get access to their publications. I think we'll mention that a bit later. Everything that we have been doing is based on the Mistral 24B, which is kind of compromised, but you will see that later. And the system that we'll provide to the community will be fully accessible via a web platform, also APIs. We'll as well release in the coming days or weeks, maybe, all the model data set that we made. And on the right here, you see the main characteristics, capabilities of the model, but I think my colleagues will provide a deep dive on those in the coming minutes. And with that, I think this is my last slide, I think, to introduce a bit the overall context. And over to you, Àlex.
Thanks very much, Nicolas. Do you hear me well?
Yeah, go ahead.
Okay, so let me give you just a very quick idea of the high-level process first on how it works. So I think most of you are already familiar, but let me just clarify the terminology at least. So the main components when we're talking about how an LLM works, obviously is going to be the prompt, that's the input that we pass to the LLM. The context window is going to be the maximum amount of text length that the model can handle. This is capped by the architecture of the model, so it's quite important in terms of long-form instruction following that kind of tasks. A token is a piece of a word, which usually is something like a 3/4 of a word that we create, and we train the model to actually understand, so that we don't have an infinite representation in a dictionary. And then the completion is the actual output generated. So as I suppose you all know, LLMs internally work in what we call an autoregressive way. So the prompt, the input, is going to be fed to the model. We're going to have these layers computing the weights, and then the actual final softmax over the vocabulary of tokens of the model. We're going to sample through it, generate one token, add it to the input, and then repeat. This is the autoregressive process itself. And obviously, this is a probabilistic model from the sampling of the vocabulary of the output layer. So therefore, it's only a matter of the most probable within the probability. Within these LLMs, there is a very clear trade-off in terms of the performance versus the cost, and cost can be measured in several ways. So here specifically, we're measuring cost as the number of parameters. And we are mapping accuracy on MMLU. MMLU is one of the most basic general purpose benchmarks on natural language processing. And you can see that we have things like Llama 8 billion or Mistral Nemo, which is 12 billion parameters on one side. here we have extreme, 400 billion llama, etc. So of course, what we want to do is to be as much as we can in this corner of efficiency within the trade-off. And considering the partnership with Mistral for this project, of course, we started with the selection of the base model with which to continue the fine-tuning. So these are the current state-of-the-art models from Mistral. Considering that the model needs to be an assistant, as Nicolas said, we cannot go to extreme specialist models like CodeStral, for example, which is an only code assistant model. Instead, it needs to be a general one. Within the trade-off that we were mentioning between performance and cost, essentially, we limited the choice to these four that you can see here, Mistral Small 3.2 and the Ministral series. After some evaluation and some comparison, then we considered that Mistral 3.2 was the best, the 24 billion model, and so we started with this model, the work. And here I will just give you a very broad idea of how EVE works, both at training and inference at a very high level. So we start indeed from this open weight LLM, which, as I said, is Mistral Small 3.2 24 billion. And then to this open weight LLM, we gather some Earth observation and more broadly Earth sciences domain data, which we scrape from the internet for the most part. And we also get general domain data. This is not Earth observation, this is just general domain. This is what we call replay data. So this is data that the model has already seen in its pre-training. And we essentially add it together to the Earth observation data to avoid any kind of catastrophic forgetting or drop on general capabilities of the model. So with this Earth observation data, we do something called synthetic generation, specifically for instruction following. So these are things like question answer, summarization, tool usage, etc. And with these two things, we do instruction fine-tuning, which is a supervised fine-tuning technique, which results in what we can call the EO-instructed LLM proper. This EO-instructed LLM proper, we have also some preference data, which is essentially a selection of preferred versus non-preferred answers, mostly around elements of style, form, and so on. And we perform alignment over this instructed LLM. And we get to the actual aligned LLM proper, which is what the user really is going to see. At that point, then, a user query is given to the model. The model is connected to several tools. So right now, it's only RAG databases. These are collection of documents, but it can be any other tool, such as a coding IED, a calculator, or a computer vision model that can be queried, for example. And then after the querying of these tools, the result of these tools is integrated into the model, and the model output is actually presented properly to the user. So let's go more in depth now on the data element, and for this I give the floor to Jino.
Yeah, thanks, Àlex. So in terms of data itself, that is including stuff that we scrape from the internet and the synthetic data that we generated, I would put it into these 6 elements per se. So for the overall text corpus itself, that is the first row that you see. It's divided into 2 components. We had 5.7 billion of them, which were open access. That is things that we scraped from internet, mainly from EO web pages and so on. And we also had about 1.1 B tokens of closed access, which came from Wiley. And for SFT, so SFT is just supervised fine-tuning instruction-based data set. You can see the format there to the right side. That is, it has an instruction and it has an input and an output. So that was like about 5K samples. We also generated about close to 100 million samples of synthetic data, which were all grounded from the corpus that we had. And that is also of a similar format. That is, you have an instruction, you have an input and an output. So preference data set is what Àlex was kind of talking about. That is, for every prompt, it has a winning or a losing response in which a human basically evaluates and sees what response wins over the other. We also had 5K samples for this. And for the building the RAG database itself, we had close to 300K articles documents, which were just small pieces of chunks that we used during ingestion. And we also had 1K samples of a hallucination data set that we put together, which is just you have a instruction or a prompt, you have an input, and you have the hallucinated response for that particular input and a justification for why it is hallucinated. Next slide, please. Yeah. In terms of breakdown itself on a more granular level, so these are the sources that it came from. So the green ones that you see are all open access one, that is MDPI, Copernicus, and NCBI, archive format, and so on. And the dark blue that you see, the YLECA, is closed access, and this is a breakdown of all the tokens that we had. Next slide. Yeah. So in terms of the overall corpus creation workflow, I'd put it into 5 stages majorly. So the first obvious stage is we kind of manually identified very high signal, very high quality sources from the internet. That is web pages that were manually selected by us and websites and so on. And for scraping itself, these days, a lot of websites have different formats, and some web pages you need to click to advanced, some pages you need to scroll, and you might have tricky captchas and all of that. So we designed our own pipeline. So we use Selenium as a driver, and we use Bright Data as a proxy to avoid rate limiting and so on. And we were able to scrape almost all the web pages, and the next stage is basically just extracting text from those. So at this point, you already have PDFs, you have JSONs, you could have HTMLs. So you need to unify them into a format. We chose Markdown. And the processing stage itself would be cleaning any sort of weird artifacts, low signal elements, and removing duplicate segments, duplicate documents as well. And we also had a PIL removal stage. We also collected metadata for each of these articles, and we put them on an RDS. And we are working on open sourcing the corpus as well as the code database. Next slide, please. Yeah. In terms of compliance, I spoke about this, but in the PIL stage, we remove if any the author names, emails, phone numbers, and so on. And we make sure to use only the permissive sources. And we also make sure to keep attribution and credit the source for whatever we've used. Next slide, please. Yeah. And for the instruction data set itself, so how we created them, we had about 20 to 30 academic annotators helping us put together this data set, and we had about 5K samples across these blocks. That is, we had 5K samples for QA, 5K samples for factuality and preference. The usage was mainly twofold. One is the obvious evaluation of the LLM, which we trained and we want to see how it performs. And for the synthetic dataset creation itself, because all the synthetic data that we create is more or less grounded from the corpus that we kind of put together here. Next slide, please. So I will let Antonio take over for the synthetic part. Yeah.
Okay. Hello, everyone. Nice to be here. Okay. So now at this point we have a nice corpus of Earth observation data, but still this is not enough to train our model, because the goal is to make the model capable of resolving Earth observation tasks as Q&A, summarization. So like just documents that talks about Earth observation are not enough. An important step is to generate a synthetic Earth observation instruction. So instruction data, with instruction data, we intend everything that is not just, let's say, a report or a journal. It's something as Q&A. So for example, instruction data are like, can you please answer to this question about this topic, or can you please summarize this? These are instruction data. And why do we need to generate this synthetically? Because the web and in general, like the literature is plain of corpus of literature review and so on, but misses of instructions. And to do this, we leverage a technique which is really used, let's say, in modern large language model, which is using another language model to generate data. And of course, the main problem of this step is to generate data that are reliable, because of course we are going to train a model expert in Earth observation. How another model be expert in Earth observation to generate this data? So the way of solving this problem is grounding the generation over some Earth observation content. And as we saw before, we have this corpus, which are like, which is a curated corpus we selected from authoritative resources. And what we do is to ask another language model to use the information contained in the corpus to generate this instruction set. And in this way, we are sure, or we are within a margin of error, sure that these instructions are, in a certain sense, they are reliable and can actually contain information that are not hallucinated. So in the next slide, we can see actually a high overview on how this was made. So as I said, as input to our generators, so we have a plethora of models as Mistral, meta models, OpenAI models. And to this model, we instruct to generate samples. And specifically, the pipeline pool that we will see later contains a lot of these instructions. So we instruct another model to generate samples. And these samples are the instruction that I talked about before. And to do this, we integrate documents from our corpus. So we instruct a model to generate instruction grounded on documents that we know are reliable in the field of Earth observation. We also run another step, which is an evaluation, because, I mean, the model has almost complete liberty on what to generate. So even though the generation is grounded, still we could have some samples that maybe are not so good, because the model maybe try to come up with some hallucinated content. Or also, maybe the generated sample is not really informative, because probably it does not talk about Earth observation, but just it focuses on other kind of information that are not really relevant to the field. And in the next slide, we can see some kind of pipelines that we implemented. I will go a bit into this. So the first pipelines that we have, which are, I think, most of the data that we generate, are question and answer pipelines. So we create a lot of this pipeline because an important thing to remember in this synthetic data generation is to have a wide pool of instruction and of type of question, because otherwise there is the risk of just targeting a really subset of Q&A. And here we can see, we start from a simple document base where we just ask to a language model to generate a question about the paper, about a survey. And from that simple scenario, we also reach more complex scenario, like the multi-document pipeline, where we create a question that could be answered only combining the content from two papers. And of course, this is like a way more complex task, because the model needs to understand where is the content from which paper, and also it needs to create a question which is sound and is not, let's say, artifact. So it's not like that is composing just random information from one paper to another. Alongside this, we also used this other pipeline from this really recent paper called Active Reading, where it also generates instruction. And to do this, what it tries to do with this paper is to come up with a learning strategies. So let's say that a document is given an input, and the model tries to come up with different instructions, like create a roadmap to learn this document, or for example, which are the main concepts over these documents. Another thing that we are doing is just giving the raw pre-trained data, so just the corpus as it is, without any instruction. And as we saw in the present, in the last slide, we saw that we are evaluating all the samples that we give to the model through another model to double check the quality of this. Okay, so the final data mix, which is actually probably one of the most important hyperparameters that we decide to train our model, is composed as we saw. So we have 17 billion tokens about Mistral data, which are divided into replay data that, as we talk, are mainly there for keeping and preserving the model's capability, which also, like, a subset of these are just about space. And plus we have 10 billion tokens about our generated Earth observation data. And there you can a bit see the division in this. So how we run fine-tuning over this? So the main idea was to define a goal, which is, of course, it's improve the capability of the model over instruction for observation. To do this, we defined metrics and benchmarks that we will see later. And what we've done is an iterative approach. So the goal of this iterative approach was to start generating a little amount of data, seeing the results, the signal that we got, and after iterate over this. So if from a certain data we got a good signal, okay, we continue generate until we see that there is a plateau. In that case, okay, maybe we have covered that use case, and maybe we can have more variety in our data, and so we try another pipeline. And this was a bit the loop that we have performed over the last months. Talking a bit about computing, which is also an important part, we had access to different computing. So specifically, Mistral also supported us with their computational, with their HPC, but we also used, let's see, public infrastructure called the Mare Nostrum, which is an HPC available for in Europe. And also we use some private cloud computational resources as Rampod and Lambda Labs. And these three main sources covered all our needs in terms of data generation, in terms of fine-tuning, and also the data processing pipelines. And also, like, we computed, which I think it's really cool, we computed the total equivalent in terms of CO2 of the entire project. So you have to think really from the first phases to the training to the synthetic data generation, which is about 25 homes for our energy, also driving a gasoline-powered passenger vehicle. And continue. Yeah, here we have it the workflow, but I will leave this to Jino.
Yeah. Okay. RAG. So RAG is actually one of my favorite topics to talk about. So let's try and motivate why do we need RAG itself. So now that we have an even struct model trained, so let's say we finish training this in 2026, and you kind of still want to make it usable like 5 years into the future, but you train the model in 2026. So there is this information cutoff, and probably in the next 5 years, there's a lot that's gone on that the model is not aware of. So can we still make this model useful and not hallucinate on random facts? So that's kind of where this RAG comes into play. So RAG is ideally a technique that aids the model in having access to more of these recent information. So the model is more factual in terms of the response that it gives and kind of does not hallucinate over. So I would put RAG into these two major phases. So the left block that you see here, that is starting from the data sources, that is the ingestion phase. So what happens here ideally is, so everything that we scraped from the internet and you've cleaned them, now you want to divide them into smaller blocks or smaller text segments. We'd call them chunk. And you want to create embeddings out of them. So embedding is essentially just you take these textual formats and put them into vectors of numbers. And once you have these embeddings, you can kind of ingest them into the vector database. To the right side is where the actual retrieval itself happens. And that's kind of where the name comes for RAG. So if you look at the rightmost element, that is the user, he comes in and he asks for a question. So this query is first put through an embedding model for which, again, you create embeddings. So again, these are just vectors of numbers. So this vector is kind of queried on the vector database itself, and you retrieve the let's say the top 5 relevant documents. And now these most relevant documents, along with the user query, is now fed to the model. And now the model has full freedom of deciding what specific chunk that it wants to use to generate the response, and gives the answer. This is in a nutshell of how RAG works. Next slide, please. Yeah, and for our DB creation itself, so we had categorized them into 5. So we put all the open access ones, which is like close to 270K, as a separate DB. The closed access one was put in a separate DB. All the ESA collections were put in a separate DB. And users in our platform, users also have the ability to bring in their own documents. So for that also, we had created a separate DB. And everything else that came from online polls and websites, we call them online curated sources. We had about 24 of them, and we maintained a separate DB for them. So for the models itself, we had a 2-stage for them. So for the embedded model itself, we used Qwen3, which is a 4B embedding model, which was on top of the MTEB leaderboard, and it performed really, really well for our specific data. And for the re-ranker, we again used the Qwen3 family, which is again a 4B billion parameter model. So to create these chunks, we had 2 major things that we did. That is, first is the hierarchical chunking. That is, if you take an article, I'm sure that there's going to be headings, there's going to be specific sections like abstract, introduction. So you want to split them in a way that you don't, that you maintain the integrity of each of these sections. So that's kind of what we did in hierarchical-based chunking. And we also divided them into meaningful chunks. We had a set limit for this, because we did not want to randomly split these chunks, so that And for the metadata itself, we use this API Crossref. And so Crossref is this non-profit organization which mapped a DOI to all these metadata, and we were able to collect things like URLs, titles, journals, publishers, license, years, and so on. Next slide, please. Yeah, so hallucination detection is kind of the last component that we had in our system. That is, given the user, let's say the user asks a question and now your LLM has given the answer. Is there a way that maybe the model has given a hallucinated answer? So can we try and find this? So if you look at the Eve block to the left side again, so that's kind of where the flow starts. So Eve is again our LLM, Eve instruct is our LLM model that we trained. So it gives an output, and we have this classification or a flagging layer here, which identifies if there is a potential hallucination that has happened or not. If it has happened, we go through this phase called reprompting or requerying. So one possible cause for hallucination could be that, maybe the retrieval did not perform well. Maybe it just retrieves some random chunks. So the idea here is that given the query and the context and whatever particular spam was hallucinated, can we kind of rewrite the query in such a way that maybe this time the retrieval kind of retrieves the right chunks? So now we have a different sort of query that is rewritten, and now that is again queried either to the vector database itself, or maybe we also have this feature of querying the web, and we get new chunks, and it's again passed to the model and given the final output. So the last bubble that you see here, that is the looping construct, which is currently not part of the system, but can be thought of an extension. So in our case, we just stop at time step 1. But let's say that I did this over 10 steps. That means you have 10 different reprompts, and you'll end up with 10 different answers. So a possible extension could be that, can you rank these 10 different responses in the order of the most relevant to the least relevant, and just give the top re-ranked one? Yeah, so that's essentially what this does. Next. In terms of results, we calculated F1 scores on a data set that we put together that we initially kind of went through. And they were about 2K samples, and we kind of tested them across very similar family of models, about 5 of them. And in case of even struct, it kind of performed really well. And this was already a very good signal for us that the model was doing well and the pipeline itself was working. Yeah, next slide, please. Cool, I'll let Antonio take over again.
Okay, so for evaluation, the main two sets of evaluation that we ran were general domain evaluation and Earth observation of science evaluation. So why do we need these two sets of benchmarks? So the first one is to be certain that the model is not losing its general domain capability. Because of course it is nice to have a model which is suited for Earth observation, but we also want to retain the capability of the model. And to do this, we need also to track these metrics. Because of course we can expect a drop, but we must also, let's say, limit this drop of performance in general domain. And after, as a second set, we have Earth observation and Earth science benchmarks. So these are, of course, the most important benchmark for us. And we came up with these 5 different benchmarks plus the A/B testing. And the important things here is that all these benchmarks that you see here are, let's say, made from scratch. We use a human annotation. We have done different rounds of post-editing to check the quality of this. And so these are created from scratch. And I think this is also one of the most important and useful contribution that the HEIG project has made to the community, because like in our different reviews, there are a lot of benchmarks in EO about vision, that for sure, but really a few about the text and in general knowledge, factual knowledge about observation. So I think that this set of benchmarks could also really useful, also like in future to understand how general purpose model perform over Earth observation. So here I will present the general domain benchmarks. So specifically, we see 3 groups of bars. So first thing, we see MMLU astronomy. So as we already saw, MMLU is general domain benchmarks that covers really a lot of topics from physics to maths to biology. And specifically in the first group of bar, we just saw the astronomy subset. And as we saw in this general domain, but I mean, in this case, we are seeing the subdomain that we are interested, we are gaining 6 points. And in the general benchmark, so in MMLU total, we can see that we are and same, we didn't have any real gains or any real drops. However, we can see that in GPQA, which is another benchmark similar to MMLU, this one is a bit more hard in a sense. And we can see here that we have a drop of performance. And this is, of course, something that we can expect because the capacity of the model is limited by the number of its parameters. So if we are injecting new knowledge about Earth observation, of course, it's a bit too much to think that we will not experience any kind of drop in general domain. But still, it's important that across MMLU and GPQA, we see that on average, the situation does not drop too much. While the benchmarks that we aim to actually have an improvement are this one about Earth observation. Specifically here, we are seeing a snapshot of all the benchmarks that we have. And we can see that for each group of bar, the first 2 represent, the first one is EVE, our instructed model. The second one is Mistral, which is the baseline in a certain sense, which is the first competitor that of course we have because we are fine-tuning of the model. And after you can see the other 3 bars are 3 other really popular models that are in the same range size. Also because we want to compare our performance across models in the same, with the same capacity. And as we can see here, in all the benchmarks, we are for sure better than the baseline, than Mistral. And we can see that like both in open-ended, which is the last group bar, and also in MCQA, the first two instead, we are better. And we also see an improvement over the other model as Quen, Gemma, and Llama Scout, which are, and this model also, they have a little bit more capacity because, for example, Gemma is 27 billion model, while Quen 3 is 13 billion model. And this a bit tell us that with a bit of loss in terms of general domain, we can really tackle the Earth observation domain, and we can see really an improvement over this general purpose model that we see here.
And maybe I take this. So to give you a little bit of a general overview then, the main takeaways, first is that what we are presenting is a suite. So first, we're presenting the domain-specific LLM, which, as Antonio said, is particularly good at Earth observation and Earth sciences, but doesn't have any kind of dramatic loss in general capabilities performance. Then also, as Jino presented, we also released the authentic and the synthetic Earth observation datasets. So both the curated, processed around 3 billion token corpus, which is the part that, due to license, we are allowed to release, as well as the around 5,000 samples created for evaluation in a variety of formats. Then we can also release a very large part of the code base in terms of the data, both the scraping and the processing, the evaluation, how to build the RAG, etc. And then, as we were saying at the beginning, the actual pipeline, both regarding the web GUI access as well as via API. In terms of limitations, we have seen the most limitations regarding the actual fine-tuning of the model. The first one is that we already are starting with a pretty high baseline score compared to models in the size range, which is good. It means that our choice for Mistral Small 24B is a very good choice. So we're already performing by default quite well on the domain. And of course, the main issue is that training with only open access or nearly only open access data means that it's quite likely that the model, it's almost certain, that the model has already seen the data in one way or another during the pre-training. And that, of course, limits also the amount of gains that we can have by showing it again, even in different formats and better structured. So right now, as we are, for the most part, wrapping this development part of the project, we are going to add to this a human preference A/B testing, as well as system-wide evaluation. So that means in the previous benchmarks that Antonio showed, also evaluating how the requerying and the RAG improves, so the entire system as a whole. And those are the last points that we are working on right now. And I'll give it to Nicolas now to give a bit of a demonstration explaining the videos.
Maybe you can play the video right now. So basically the system will come as another, say, chat with different panel on the right, on the left. Here I will give two of the capabilities. So on the left, you can describe what I can do. If you cannot do that, like image retrieval, or just text-based information. You can, of course, log in through your own profile, fill some information, then as it was mentioned by Antonio, we have developed this to compute the overall CO2 emission that you made through different methods, which is what I think the situation and the impact on the planet. Then, of course, there's information about us, how to contact us, and also some privacy policy notice, which are also well described so that you understand a bit what are your rights and how data would be transferred or what not transferred, so on and so forth. You can, of course, control the way the LLM will be behaving, let's say, and for instance, control a bit the degree of creativity and deterministic of the model through these so-called temperature parameters ranging from 0 to 1. You can also set a kind of threshold for the RAG system, so that the retrieval works. Give more freedom to give more flexibility to the retrieved documents. You can set the maximum document that will be retrieved by the RAG system, years, journals as well that could be specified, and also the minimum citation of the paper that you want the system to retrieve. Could be set to 100 or whatsoever, so that you ensure that you have very high cited papers and maybe quality as a proxy of the number of citations. And as it was mentioned beforehand, we have as well access to different collection of information through the raw system. So as we mentioned, we had a collaboration with Wiley. We have as well Wikipedia. We have as well the EVE Open Access that was basically the database that was shown before, and all this ESA documentation for which you can enable and disable as you wish. So you can, as you can see here, enable and disable the things. You can also ingest your own collections. So that actually when you will prompt the question, then it will directly integrate the different documentation that you include within the RAG database. So it's just the process to create a specific collection whereby you can actually drag and drop your own files into the system so that you can directly interrogate those. So with that, maybe you can directly switch to the next presentation, which is here more linked to how to use the system. Again, it's like very standard for trust system. While you have, of course, the history of all the interaction that you had with the system before. So you can click on one specific one, like, okay, tell me which new space actor is providing methane detection. Then you see the response with different elements, which is showing like that. You have as well some nice table. As it was mentioned, providing the sources is super critical because I think we all want to get, let's say, the true information and the raw information. So here you can click on the relevant papers and access to the proper documentations directly through the different publishers. And of course, you can ask any new question, like on this one, explain in 10 points how deforestation impact climate change. And again, while you have to wait a little bit, the system retrieve the right documentation and then synthesize from the model the answer. And again, well, I will not go through the response, but an important thing is again that all the response provided by the system is grounded by sources that you can click and check if they are, let's say, compliant or in line with the main message that was given by the systems. You can also retrieve the chunk that appear as the most, let's say, relevant for the prompt. One aspect that was mentioned as well beforehand is the capability for the system to detect hallucination. And here this is an example whereby, okay, you ask what is a CubeSat with different, let's say, answer that could be a bit vague, let's say, on what is exactly a CubeSat from a pure definitions. And here you will see that the system behaves pretty well in the sense that here, first you will say, okay, this is a class of smaller satellite based on 10 centimeter cubes. But if you check for the hallucination, it will say that, okay, there might be maybe a vague, let's say, definitions. So then it check and then it will, let's say, precise, let's say, the answer and say, yes, it is partially true, it's partially right, and then provide some more factual element as an answer to these tricky questions. So I guess you can stop the video. Àlex, I think I'm good with these slides. The process was this one. I mean, we had this development of this EVD system in 1925. We had a pilot phase whereby we invited, I think, more or less 300 users to test the system, for which we are now analyzing the results, so that will improve the system in 26. As we mentioned before, everything will be more or less, well, open source. I mean, the model for sure, the data set for those for which the license enable the disclosure. Then the benchmark as well will be disseminated, as well as the technical paper that will describe very well all the developments. We aim to make this system fully operational in likely in Q2 this year. And as it was mentioned before, I mean, again, as of today, the system is a pure textual, let's say, system, but the clear evolution of what we'd like to do is to act more like as a reasoning top layers that can then trigger different tools. Could be geospatial tools, GIS elements whatsoever, also foundation models, could be database of, again, publication, but it could be as well calculators or whatsoever piece of codes. And I hope that by the end of this year, we may have something cool to demonstrate as well on that field. So yeah, if you have any question on this presentation, of course, you are more than welcome to drop an email to us. And so thanks a lot for your attention. I don't know if we have time for question. I mean, we are just on time, but maybe you have some question in the audience. Go ahead.
Really, really fantastic presentation. I would say you guys could probably do like 3 hours on how much content you were able to sort of squeeze into this 40 minutes. So thank you so much. I'm going to immediately say that we need to have another call from you guys, another lecture once this thing becomes operational, as you mentioned later in this year. I'm blown away. Like, I'm already imagining so many uses. We're already at the top of the hour, so I don't want to like keep you guys. I know it's already pretty late. I do have some questions. What are your thoughts though on like potential integrations? Are you thinking about ways in which this is really sort of open and like integrated into like something like QGIS? Is that where you want to go as well? Or are you imagining this is mainly as a web platform where you have individual workflows that you're kicking off and then you're interacting with this more top layer? Where do you guys see this going?
Àlex, would you like to react first? Maybe I'll give my 2 cents after.
So indeed, we are planning for 2026 as soon as we open the system to step on the gas, particularly on the integrations. So I would say that there are going to be probably several different kinds of integrations. One kind of cluster of integrations probably is just going to be more documents and more data. There are a lot of additional knowledge bases that we can either create or connect to, which is always very, very important. So you can imagine a very large amount of collections divided by topic, thematic, etc. There is also an important part that is an agentic connection to, for example, websites in terms of protocols, standards, formats, things like this. One of the main issues with RAG is that the data that you scrape, you put in a knowledge base, and the model sees it all together, which sometimes versions that overwrite previous documents, the model should not see. So that kind of connection is quite important. And then indeed, connections to models that the model can query to perform, let's say, object segmentation on a given input, or processing of data, as well as repositories of raw data like Copernicus Hub, etc. All of this is in our objectives for this year.
As a complement, I mean, on our side from ESA F-lab, we have been developing a few foundation models this year. I mean, you may have heard about Terramine, which is as of today only, let's say, a computer vision based foundation model. There was a bit of initial step to make it, let's say, more like a VLM model, combining with, for instance, caption that we did with Llama, and you may look at the interface of Terramine. But this is clearly like an extension for me, like I said, to really bridge the gap in between the pure computer vision and Earth observation community with kind of, again, overlaying layers that can directly interrogate through foundation model and VLMs, the different databases. So this is for me like a strong axe of development, let's say. But I hope there will be some element in 26. But then, yeah, the matter of, let's say, integration of, let's say, this tool within QGIS or any GIS software, I mean, we leave that to to external entity. I mean, everything will be provided. We'll provide the tools, the codes, and everything. So I think this is left to the whole community to do this integration. As of today, we ESA will just, I mean, we'll take Eve as it is and then plug in different tools, let's say, within the Eve system as it is.
Amazing. Yeah, I'm thrilled that you guys are also mentioning that this platform is going to have like an open database, and all that thinking is so crucial for that next wave of folks who want to do that integration. So that's amazing. Biplav, do you have any questions? I don't want to hog the mic at the very end here.
Thanks so much. I do have some questions, but maybe we can take it offline. I was just interested in learning more about your ML ops side of things, and maybe some insights into context engineering, because I see you're using like a lot of data source, and with the RAG itself, there are different ways you can design your context. Yeah, so if you could provide some insights on those.
Yeah, so about the integration of all these sources, yeah, for sure is a topic. And yeah, we tried to run like most, that there was like a lot of engineering trying to integrate all the context from the different sources. And specifically, you are interested into a specific topic that maybe I can better clarify.
No, I was just because you use some of the Mistral models and they have some context window. And you're also mentioning like you have all these documents in place, and you need to update those documents too. So context gets really large, right? So
yeah. So about this, no, okay. Yeah, we actually spent a bit of time to actually manage this, because as you said, context can really, even though like it seems that this model have infinite context, when you start to actually give them documents. And also you have to think that this is like a chat system. So you also have previous turn, and previous turn also have their context. So it starts to become really, really a lot. And probably in 2, 3, 4 turns, the context window is already gone. So what we have done in this case was to allocate specific context length for each part of the turn, for example. So for sure, the most important thing is the current turn, for sure, because otherwise the model does not know what is the current answer. And after, what we try to do is try to squeeze the previous conversation. So one way to squeeze this conversation, for example, is summarization. We do a summarization of the conversation so far. Another way, in RAG, in retrieval, documents have a score, have a similarity score. So another way to do this is to limit the number of documents that it receives. And maybe you start trimming for the less relevant documents. So yeah, this is actually one of the most important aspects of the entire chat system.
Yeah, I mean, yeah, I think that kind of makes sense. Even within the number of neighbors, you need to decide like how many neighbors it would capture and all those kind of things, right? Because yeah, so that kind of makes sense. Maybe one last question on the metrics. I know you talked about F1 score, but since it's an LLM, so you're getting answers in words, not just numbers all the time. And like in spatial context, we use F1 score accuracy for our models, but for LLMs, there are like lexical scoring like BLEU or ROG that are mostly used to see like how similar the output is. So did you try incorporating some of these like lexical understanding within the model, or was it mostly like F1 score?
So maybe we can go back to the evaluation slide. So in terms of benchmarking a language model, let's say that we have two big, let's say, families on how you can benchmark. So here you can see a clear division between open-ended and MCQA. So in open-ended, as you say, The basic is to use this metric as BLEU, BLERT, BERT score that tries to evaluate open-ended generation. And we have done this, but not using this metric. I mean, we have done some tests, but the best method, and it's also like the most popular right now, is to use another large language model as a judge. So you use another model, you give the target answer, and you ask according to your metrics. Also, because this is also one of the most difficult things to do in a large language model. Try to understand what you are measuring.
Yeah.
So with the evaluator, you want to try to understand if you are measuring the model's knowledge, the model's capability of generating nice text, to have like a well-formatted text. So we also spent a lot of time to try to do this. On the other hand, multiple choice question answering is really useful because you are, in a certain sense, certain. I mean, of course, with a bit of error, you are sure that you are measuring the actual capability of the model. Because in this case, you just ask the model to choose between an option. So in MCQA, you have a correct option, or in one of our benchmarks, you can have like several correct options. And in this case, I mean, the model, you don't have to judge something that is hard because maybe the format uses similar terms. You just have an option that you must decide which is the correct one. And to evaluate this, you can use some regex, or just you can be really strict on the prompt and ask the model just to ask to output the correct answer. So that's why you see scores as F1 score, because F1 score is about the correct option. So it's like you're doing a classification task. So, but instead of having, let's say, a soft max and after you take the most probable, let's say that it is about text, but in a certain way, and this is done in language modeling. You do the same with the probabilities of the character A, B, C, or D. So, for example, GPQA actually uses metric the logarithmic probability, but also other instead they just rely on free text and do some regex. So that's why you see F1 score. It's not about open-ended, but it's about MCQA, which is saw as a classification task.
Cool, thanks. Yeah, that makes sense. Yeah, looking forward to playing with the system. It looks really cool.
Nice.
Yeah, I'm just blown away, and I will reach out about a future opportunity for you guys to present again, because you guys are developing so much, and you've got us all really excited about this upcoming year. So thrilled again, fantastic presentation, and I thank you for staying longer because I know we've already gone over. It's a little bit later for you all, but thanks again, and fantastic presentation.
Thanks a lot. It was our pleasure.
Thank
Have a
you.
good day. See you soon.
Thanks, everyone.
Ciao, ciao.
Bye, everybody.
Bye.
Thanks.